Good morning, everyone. My name is Fabrizio Greco from the University of Calabria, and the title of my presentation is Stability Analysis at the Micro and Macro Scales in Periodic Bioinspired Composites. The work is co-authored with Andrea Pranno, Umberto Maio, Raimondo Luciano, and Lorenzo Leonetti. The presentation will cover the following arguments. Firstly, I will start by introducing the topic and the motivations of the work. Next, the theoretical determination of the nonlinear static and dynamic behavior of composite materials undergoing large deformation is recalled at both the micro and the macro levels by using nonlinear homogenization and the incremental wave propagation theories with reference to a finitely predeformed microstructured solid. Particular attention is devoted to the stability analysis at both the micro and macro scales, which are strictly connected to the wave propagation problem. Then the numerical implementation of the macroscopic and microscopic stability analysis by using a finite element approach will be discussed. Subsequently, some numerical application involving innovative necro-like composite materials will be illustrated. The presentation ends with some concluding remarks and discussion about future developments of the activity in progress in the framework of the multi-scale analysis of incremental wave motions in finitely deformed periodic solids. Composite materials as bioinspired and metamaterials with both mechanical or multiphysics properties are used in many engineering applications by virtue of their better performances compared with conventional materials and arising by the hierarchical microstructure and also by the effects of the different scales involved in the problem. For instance, acoustic metamaterials such as phononic crystals are used as sound filters, acoustic wave guides, vibration attenuation, isolation devices. Moreover, bioinspired nacre-like materials arranged in a brick-mortar pattern may be used for next-generation individual protection devices. Since these materials are often adopted for extreme and advanced applications, they must be able to undergo large deformation without loss of structural integrity. When subjected to high level of loadings, composite materials reinforced by fibers, plates, or particles and arranged in according to a periodic or random microstructure may exhibit instability phenomena at macrostructural scale. These phenomena are usually considered as a precursor of failure, also due to their strong interaction with other microscopic damage processes. These nonlinear phenomena may occur at both micro and macro scales and may have a static or dynamic nature. The exact determination of the nonlinear response is still a challenging task, and accurate results could be obtained by only by using a full-scale direct numerical simulation. But the associated huge computational effort makes this kind of analysis unpractical for real-life application. And this situation motivates the necessity to introduce efficient multi-scale homogenization approaches in order to predict the onset of failure in these materials by investigating their macroscopic behavior. The composite material here analyzed is assumed to have a periodic microstructure described by suitable representative volume element RVE. Each constituent is characterized by an incrementally linear constitutive law relating the rate of the deformation gradient tensor to the rate of the first Piola-Kirchhoff stress tensor in terms of the tangent moduli tensor. The RVE is subjected to boundary conditions depending on the macroscopic deformation gradient, and the solution of the corresponding nonlinear equilibrium problem for the microstructure gives the macroscopic first Piola-Kirchhoff stress. The micro and macro scale are in fact coupled to each other by means of the classical relations that define the macro variables in terms of deformation traction on the boundary of the RVE. By splitting the microscopic deformation field in a linear part plus a fluctuation field, it follows that an integral constraint must be imposed on the fluctuation field, and according to the periodic nature of the material, this constraint can be satisfied for enforcing periodic deformation on the boundary of the RV and antiperiodic traction. Now we are interested in studying the incremental homogenized response of the composite material. The variation formulation and associated equation for the equilibrium problem driven by microscopic deformation, both the global form and the rate form are here shown. Once the incremental problem is solved, the microscopic constitutive response can be defined in terms of the so-called homogenized tangent moduli tensor, which is represented by an overbarred CR. It is important to note that the equilibrium configuration of the microstructure is not, when is not incrementally stable, the one-cell homogenization approach is no longer valid, and a larger assembly of unit cells must be considered to obtain the constitutive response, the homogenized constitutive response. The stability condition at a given microscopic deformation is here studied based on the positivity condition for the stability functional S for every incremental deformations satisfying the periodic boundary condition. The primary instability is detected when the minimum eigenvalue associated with the stability functional first vanishes. It is important to note that a classical microscopic stability analysis based on the strong elasticity for the homogenized moduli tensor is not usable in general, since it provides a non-conservative estimation of the primary instability load when the instability mode is local in nature. The numerical determination of the critical load levels and the associated mode shapes has been carried out here by using a one-way coupled total Lagrangian finite element formulation, able to determine the principal solution path for the analyzed unit cell assembly in coupling with the accompanying eigenmoduli boundary value problem, giving the instability critical load effects in a sequential way. The geometry of the analyzed two-dimensional unit cell is referred to a typical nacre-like material and is formed by reinforcement in the form of stiff platelets embedded in a soft matrix material and arranged in a brick-mortar pattern. To solve the problem, a specific script code has been developed by using the commercial code console multiphysics for the computation, and the microstructure constituents are supposed to obey a quasi-incompressible Neo-Euclidean constitutive law. The composite microstructure has been subjected to macroscopic biaxial loading radial paths in the principal microstrain space, governed by the macroscopic principal stretch ratio in the x1 direction. The microscopic stability analysis has been carried out by discretizing the variational linear eigenvalue problem characterizing the primary stability, while the macroscopic stability analysis has been carried out by monitoring the value of the load parameter along the prescribed microdeformation path, where the strong elasticity condition for the homogenized moduli tensor first fails. We start now with the numerical results by determining the critical stretch ratio corresponding to the onset of elastic instability with the long wavelength, by analyzing the macroscopic instabilities. In uniaxial compressed nacre-like composite materials, and a parametric analysis with respect to the main material and the microstructural parameters, including shear modulus, contrast, platelets volume fraction, and platelets aspect ratio, has been carried out. As can be seen in the following picture, in the nacre-like materials with low shear modulus contrast K, the macroscopic instability critical curve peaks are reached for intermediate values of the volume fraction. while for high values of K, the peaks are reached for higher volume fraction. In the general cases of low K, low values of platelets volume fraction allow the composite to reach higher uniaxial deformations before the appearance of macroscopic instabilities. The macroscopic instability curves are now reported as a function of the platelets aspect ratio W for a wide range of volume fractions. We can observe that for the cases with low shear modulus contrasts, the critical stretch ratio increases as the platelets aspect ratio increases until reaching an almost zero slope for W equal to 10. While for low platelets volume fractions, the critical curves show an initially decreasing branch until a point of minimum is reached, and then an increasing branch. In addition, for the cases with the large shear moduli contrast, K larger than 500, the critical instability curves related to large values of platelet volume fraction increase only slightly, and as the aspect ratios increases, maintaining very high values for the critical stretch ratios. By taking the critical stretch ratio obtained with a shear modulus contrast K equal to 1000 as a reference, the percentage decreases in the critical stretch ratio have been summarized in this table for composite with varying shear modulus contrast, platelet volume fraction, and platelet aspect ratio. The results obtained by performing a microscopic stability analysis carried out for increasing assembly unit cells are now illustrated for the composite characterized by shear modulus contrast K equal to 20, platelet volume fraction equal to 0.5, and platelet aspect ratio W equal to 1. The picture illustrates the behavior of the first two instability modes and associated eigenvalues as a function of the RV assembly size, increasing in the horizontal direction with a geometrical progression and a fixed number of 2 unit cells in the vertical direction. A fixed stretch ratio coinciding with the microscopic critical stretch ratio is considered. The trends of the first, which is the lowest, and of the second eigenvalue are depicted for varying RV sides in the x1 direction. The behavior of the lowest eigenvalue of the stability function shows that the prime instability mode is characterized by an in-phase pattern. The obtained microscopic critical stretch ratios are summarized in this table for each investigated unit cell assembly to compare the microscopic critical factors with the microscopic ones. The results highlight that, generally speaking, prime instability modes are global in nature, and that the difference in the predicted critical load decreases as the platelet aspect ratio W and the shear modulus contrast K increase. Results show, in addition, that the geometric and material parameters combination for which the critical mode shape is local is given by K equal to 20, platelet volume fraction 0.1, and W platelet aspect ratio equal to 10. The local microscopic instability mode, characterized by finite wavelength, has a periodicity corresponding to a 2x1 unit cell assembly, as shown in the picture. For Necker-like microstructure with K equal to 1000, significantly smaller differences have been obtained. The results are reported in this table and show that different convergence speeds can be obtained by varying the microstructure and the material parameters. The figure illustrates this observation, showing the critical mode shapes for the composite with the identical microstructure parameters and varying aspect ratio and the unit cell assembly. In conclusion, the results highlight that the critical stretch ratio and the instability mode shapes are highly influenced by both microscopic geometric arrangement and material composition. comparison with the microscopic stability analysis of the real microstructured solid have pointed out that for a wide range of geometrical and material parameters, the instabilities resulted to be characterized by long wavelengths with an in-phase mode shape. We also observed that by adopting small unit cell assemblies, the microscopic stability analysis is able to provide strong underestimates of the critical stretch ratio, while they provide similar results with respect to the macroscopic stability analysis when they are performed by adopting very large unit cell assemblies with prevalent dimension in the lower direction. Finally, the stability analysis can be based we can observe that stability analysis can be based on the criterion of the loss of strong ellipticity condition referred to the homogenized incremental moduli tensor, which is a computation less expensive than a full-scale microscopic stability analysis, which must be carried out by using a finite element approach. And only a few microstructural morphologies, characterized in particular by low values of platelet volume fraction and shear moduli contrast, together with the high values of the platelet aspect ratio, require a full macroscopic analysis. Thanks for the attention.